Hello and welcome to lesson 6.2 on inverse relations and inverse functions. Today's goal is going to be to find inverses of relations and to verify that relations are inverses by using what we call compositions. You would have went over compositions in the previous lesson. That is when we take a function like f of x and we take another function g of x and we kind of put them together. So you take one function and insert it as the variable in the other function. So you might end up with f of g of x, or if you did the opposite, g of f of x. Okay, and hopefully you're familiar with that from lesson 6.1. So let's go over this. So two relations are inverse relations if one relation contains elements of the form a comma b, when the other relation contains elements of the form b comma a. Okay, so when they say relations, we're just saying the relation between these two numbers, like a point on a graph could be thought of as a relationship between two numbers, between our x value and our y value. Okay, so they're giving those values the label a and b in this. So inverse relations would be like 3 comma 2 is the inverse to 2 comma 3. Okay, so they're inverse. Basically, if we swap the x and y value with each other, then we get the inverse relationship. Two functions, f and g, are inverse functions if and only if both of their compositions are the identity function. So those compositions were that, like f of g of x, g of f of x, and the identity function is just when something equals x in the end. We'll see examples of that, so don't worry about getting bogged down on that one quite yet. Let's look at an example of an inverse function though. If the function f and f inverse are inverses, I read this as f inverse, f to the negative first power, I just read it as f inverse, then the function evaluated at a will equal b if and only if the inverse function evaluated at b equals a. Okay, so we're dealing with an input of a and an output of b. In the inverse, an input of b produces an output of a. Okay, so similar to like how we think of addition and subtraction as equal and opposite operations, multiplication and division kind of do the same thing in two different directions. So for example, if I took a number and multiplied by 3 and then divided by 3, I end up just where I started. If I use a function, the inverse function will kind of just do the opposite. It'll take me back to where I started. So if I put in a and I get out b, well then on the inverse, I should be able to put in b and go back to a. I should be able to go like kind of back in the opposite direction as what the function did. So in this example, we're going to let f of x equal x minus 5, and its inverse, f inverse of x, is x plus 5. So the input on our original function will produce some output, and if we take that output, we'll get back to where we started in the inverse function. So let's see that happen. So f of x evaluated at f of 7 would be 7 minus 5, or 2. So my input is 7, my output is 2. On the next one, I'm going to take this answer 2, this output, and I'm going to make it my input over here. So f inverse of 2 is 2 plus 5, or 7. Okay, so over here it's an input of 7, an output of 2. On this one, it's an input of 2 and an output of 7. Okay, so they kind of take us back to where we started from. Not all functions have an inverse function. If a function fails the horizontal line test, you can restrict the domain of the function to make the inverse a function. Choose a portion of the domain on which the function is 1 to 1. There may be more than one possible domain. Okay, so what that is saying is best illustrated kind of over here in some of these pictures. Okay, so if we look at this parabola, we know that this is a function, and what defines this as a function is that every input value, every value of x, has one output. Okay, so you put in some input, like you put in, I don't know, let's look 2, and you get an output of 5. You put in negative 2, you get an output of 5. You put in 0, you get an output of negative 2. Okay, there's always just one output for every input. That's very important for our definition of a function. There's always one output for every input. Now that's what it means to be 1 to 1. Now, if I want to find the inverse of this, well, I just swap the x and y values of every point. So instead of going over 2 up 5, I'm going, or actually that looks like maybe 3, over 3 up 5. For the inverse, this one in blue, I would be going over 5 up 3 to find my point. Instead of going back 3 up 5, okay, -3, +5, I'd be going +5 and -3 to get to that point. Okay, so all of these points, if we labeled every point along this parabola, if we take the x and y coordinate and we flip those values, we get this one. Okay, we get the inverse graph. Now that inverse can also be described as a reflection over the line y equals x. So this diagonal dotted line is y equals x. If you like tilted your head so that it was vertical, you'd see that it kind of looks like a mirror that's making a mirror image. Okay, now here's the problem. If I do that mirror image, I get this guy, and this guy in blue does not satisfy that vertical line test anymore. If I put an input of 5, like I said before, I get an output of 3, and I get an output of -3. You don't want that for a function. Functions can only have 1-to-1. They can only have one output for every one input. So what we do is we basically say, well, we can't find an inverse function to this parabola, whatever this is, x squared minus 2 or something. There is no inverse to that function. There is no function that just does the opposite of what this function does. However, there are inverses to portions of this function. So if we just looked at the portion of the function where x is negative, the left side of the graph, well, the inverse of that is going to be the top half of this blue curve. Okay, so it's going to be the thing that kind of looks like this piece right here. If we look at the x values that are all positive on the original function, if we want the inverse of that one, it'll be the bottom half of this. Okay, which would be drawn, over here to the bottom half. Now, each of those halves pass the vertical line test. They only have one output for every input. Okay, so that is what is being described when we look over here. Not all functions have an inverse function. If a function fails the horizontal line test, you can restrict the domain of the function to make the inverse a function. When they say horizontal line test, they're basically saying if you put a horizontal line through this guy, if it touches twice, that means it's going to be a vertical line that touches twice on the inverse. So I don't know, just different ways of saying it, but basically, if a horizontal line can go through your original function and touch twice, it means that it will not have an inverse. There may be more than one possible domain. Okay, so that was like, we could say the domain of the inverse we could describe as a domain where x is positive numbers on the right, or one where x is negative numbers on the left. And I think that is it. So we will get started on example 1 in the next video.